Welcome to the second half of the Thursday morning session. The first talk is by Maria Cristina Baglio on X-ray binary jets and in polarimetry. Go ahead, please. I give you a warning 5 minutes before.
Okay, that's fine. So good morning, everyone. And first of all, I want to really thank the organizers for inviting me to give this talk today. Of course, I'm sad for not being there, but at the same time, I'm also really thankful for the wonderful organization of this hybrid event. So today I will talk about jets in X-ray binaries, especially at near infrared and optical frequencies, and in particular in polarized light. I will try to give you an overview of the polarimetric observations that have been performed so far on X-ray binaries, especially when leading to the confirmation of jets emission. Not that we really need it, but a very brief introduction about low mass X-ray binaries. They typically host a compact object that can be a neutron star or a stellar massive black hole, and a companion star filling its rush lobe and accreting mass onto the compact object through the formation of an accretion disk. In terms of the emission, the internal part of the accretion disk and sometimes the compact object itself will contribute to the high frequency emission of the system, while the outer part of the disk and the companion star will contribute to the near infrared and optical part of the spectrum. In some systems, the emission of collimated jets is also observed, and these jets will typically emit at radio, infrared, and sometimes optical frequencies, as I will detail later. X-ray binaries can be persistent, which is typically the case of neutron star X-ray binaries, and they maintain a stable level of mass accretion rate and X-ray luminosity during the years. Or, which is most common for black hole X-ray binaries, they are transient, displaying short periods of enhanced activity, the outbursts in which they share similar properties to persistent systems, and way longer periods of quiescence with low X-ray activity and mass accretion rate. When an X-ray binary is in outbursts, we can follow its evolution using this hardness intensity diagram that is X-ray luminosity versus the hardness of the X-ray spectrum. We already saw this diagram in the past few days, but briefly, when the system is in quiescence, it will be down here outside the graph with very low X-ray luminosity or undetectable X-ray luminosity sometimes. And then the outburst starts and the system will experience a hard state, which is characterized by very high fast time variability and hard and non-thermal spectra. And then it will transition to the soft state, where it will stay for a while with these small excursions in the hardness of the spectra. And the soft state is typically characterized by low fast time variability and soft and thermal spectra. At the end, it will go back to the hard state and then back to quiescence. So I'm a jet person, so why am I interested in these? The point is that there seems to be a correlation between the accretion and the ejection. And in particular, when the system is in the hard state, we typically see the emission of compact jets. When the system transitions from the hard to the soft state, we can see the emission of relativistic radio flares. And then when the system is in the soft state, we typically don't see the radio jet anymore. We say that it is quenched. So this scenario is called accretion ejection coupling, and it has been observed to work for several systems so far, especially black hole X-ray binaries, and recently also for a few neutron star X-ray binaries. In terms of the spectrum, this is what a compact jet typically looks like. At the lowest frequencies, we have this flat or slightly inverted spectrum that is due to the superposition of all the emitting regions inside the jet, going from the source, the compact source, to the further out in the jet. Then at a certain frequency that is called the jet break frequency, the spectrum becomes optically thin and the slope turns negative. And the position of the break is predicted to be in the infrared for X-ray binaries, and it is essential in order to determine some of the most important properties of the jet, like the magnetic field strength or the radius of the acceleration zone. So it is really important also to constrain the models for the launching of jets in X-ray binaries. The problem is not really a problem actually, but is that the determination of the jet brief frequency is difficult because the spectrum tends to vary very rapidly during an outburst. This is a really peculiar characteristics of X-ray binaries, and it makes them really interesting objects to study, because this fast evolution allows to observe in short time scales all the evolutionary stages of the jet, and then possibly to extend the properties that are derived for all the sources for which such a study is not allowed on short time scales like AGNs. So this is what we can expect to observe as a broadband spectrum of an X-ray binary that emits jets. Here we will have the spectrum that we just discussed, and then at the highest frequencies from the optical to the X-rays, we will have other components that are more dominant in the spectrum. In the optical, we will have this irradiated disk, which reprocesses the radiation emitted in the X-rays and re-emit it in the optical and UV. Then in the soft X-rays, we will have the viscous disk, and in the hard X-rays, we can see the emission from the corona, for example. So at optical and near-infrared frequencies, as you can see for this black hole X-ray binary GX39-4, if a jet is emitted, we will see an extra red component with respect to the black body tail of the accretion disk. And this is due to the optically thin emission from the jet, and it is typically referred to as infrared excess, and is one of the most common signatures of jet emission in X-ray binaries in the infrared and optical regime. So this is one possibility, but of course it's not the only one signature of jet emission at these frequencies, and in particular, going to the core of the talk, it is another possibility that we have is to detect linear polarization in the radiation that is emitted from the X-ray binary. In fact, jets emit synchrotron radiation, and the synchrotron is known to be intrinsically linearly polarized, especially when it's in the optically thin regime. So in the radio, where the signal of the jet is typically stronger, the polarization is, however, quite low, of a few percent, and this is due to cancellation effects that arise by the superposition of all the emitting regions in the jet. That is what gives rise to the flat spectrum that I already showed. Similarly, in the optical, we expect to have a low level of polarization because in the optical, the jet will not be dominant, and the other components that emit radiation are typically intrinsically non-polarized, like the disk or the companion star. So basically, we will see polarization in the optical only if the synchrotron makes a strong enough contribution so that it's not suppressed by other sources of emission. And then we will have higher levels of polarization in the infrared. In the infrared, we are observing the optically thin synchrotron emission, and we don't have a dominant accretion disk. And moreover, we are looking at the base of the jet, where so it's a small region, so we can expect the ordering of the magnetic field lines to be higher there. So in fact, the real point here is that the level of polarization will strongly depend on how ordered the magnetic field is. So if the magnetic field is tangled, for example, there will be cancellation effects, and therefore the polarization level that we measure will be low. So an important thing about polarimetry is that it really helps investigating the structure of the magnetic field in jets. That is quite unexplored but exciting field. So let's look now at some examples, first from the group of X-ray binaries in outbursts, which also include persistent systems. Here we have the microquasar GRO J1655. It was observed with a polarimeter during an outburst in the hard state, both in the infrared and in the optical. You can see from this figure here showing polarization versus the confidence of the measurement that they found some detections of linear polarization between 4 to 7% in the infrared, so not too bad. And here I'm showing instead the polarization versus frequency. So you can see both the optical and near infrared polarization. And there's a trend of the polarization with the level being lower for higher frequencies. And moreover, in the optical, the level of polarization for this source was found to vary with the orbital phase. And this led the authors to interpret it as due to Thomson scattering in the accretion disk, because of course there has to be an orbital dependency, considering that they see it varying with the orbital phase. But unfortunately, this interpretation could not hold up for the infrared polarization, because in that case, we would have had an opposite trend with lower polarization for lower frequencies, considering that the accretion disk is more dominant for higher frequencies. So in the end, the authors interpreted the near-infrared polarization as due to synchrotron from a jet differently from the optical one. Another microquasar for which polarization was detected is XTE J1550. If I'm not wrong, this was actually the very first near-infrared polarization detection for an X-ray binary. And the system at the time was experiencing a weak hard state outburst, and the authors of this work could measure a level of polarization of a few percent. And they represented it here. You can see it very well in this graph. It's on the QU plane. Q and U are Stokes parameters. I don't know if you're familiar with this representation, but basically what we do is to evaluate the Stokes parameters for linear polarization for a group of reference stars and for the target itself. Then we represent all together, and if the target is polarized, it will not cluster together with the group of reference stars. And this is exactly what we can see here in the infrared for this source. And we also have this spectral energy distribution, where just focus on the one on top. The authors clearly observed the presence of this infrared excess, because the infrared points do not follow the power law described by the optical ones. So they interpreted this as a synchrotron from a jet, and therefore also the measurement of the polarization was linked to the emission of jets. And they could also measure the polarization angle, and was found to be perpendicular to the jet axis that was known from previous radio observations. Therefore, since the polarization angle corresponds to the electric field vector angle, this implies a magnetic field in the jet, which is parallel to the jet axis, that, as you will see in this talk, will become kind of a common feature for compact jets in X-ray binaries. Now, GX39-4, this is a famous macroquasar. We've heard a lot about it in the last few days. It was observed with a polarimeter in the near infrared during its famous outburst in 2010. And significant but varying polarization degree was observed with a time scale of the variability lower than 60 seconds, so really variable. And as you can see in the spectra here on the left, a certain variability is also observed in the shape of the spectrum at the lowest frequencies from epoch to epoch, with a time scale of the variability of a few days, so way longer than the variability observed for the polarization. Actually, this very short timescale variability is reminiscent of what was found by Poshak and collaborators in 2011. This is the SED of GX39-4. They could constrain very well the frequency of the jet break in the mid-infrared, but this is an average spectral energy distribution. What they actually saw in the mid-infrared is this, as you can see in this inset. There was a huge and dramatic variability of the mid-infrared emission, with the slope also changing a lot from epoch to epoch, which means on a timescale of a few minutes or less. So a timescale that is really similar to the variability observed in the polarization. And this was interpreted as due to the emission of a flickering jet in the mid-infrared, and therefore also for the polarization, a similar interpretation was given. So the authors believe that the polarization is due to the emission of the jet, and moreover, considering the very low levels of polarization of 1 to 3%, they also infer a tangled magnetic field at the base of the jet. And finally, the polarization angles was evaluated, and again, as in the case of 1550, it was found to be parallel to the, the magnetic field was found to be parallel to the jet axis. Here is another case. It's very different from the previous ones. It's V404 Cygni. It was observed during its flaring state in 2015 in the optical this time. And here on the right, we have the optical light curve and then polarization and polarization angle curves with respect to time. As you can see in the mid panel, they found a rise and then a fall of the polarization and then a constant polarization here, while instead the flux was rising. So there's no apparent correlation between the light curve and the polarization curve. And the polarization angle was constant at around 170 degrees. That is approximately the angle of the resolved radio jet. So this is exactly opposite to what we just saw for the other sources, because this implies that the magnetic field is perpendicular to the jet axis. And this is an interesting feature because it's a condition that can go to compress the field lines locally, giving rise to a partially ordered magnetic field in that region. And this very ordered magnetic field can give the polarization, the higher levels of polarization that were actually measured here, because these are pretty high levels of polarization, considering that we are looking at the optical light. And interestingly, for that source, a radio flare was also detected a few hours after the optical polarization flare, that is this blue one here. So basically, the authors observed first the base of the jet in the optical in polarized light, and then the radio flare that was arising from emission around the jet downstream. So we are observing an individual ejection evolving from optical to radio wavelengths. That was a really exciting result. With neutron stars, life is less easy because they're fainter, basically. But we managed to find some detections of polarization, and here is the example of the persistent system for UO614. Simone Migliari and collaborators had this very nice broadband spectral energy distribution from radio to X-rays, and the infrared excess here is evident, and they also constrained the break frequency to be in the mid-infrared as it happens for black holes. So the presence of the infrared excess was interpreted as due to the emission of a jet. So we had the idea to look for polarization in the optical. And despite the faintness of the source, we managed to get a 3 sigma significant polarization detection of 3%. That is represented here in this QU plane again. This is our target, and this is the group of reference stars. And considering the broadband spectrum of the source and the power law fit that were already published, from the ratio between the expected jet flux in the R band and the measured flux in our campaign, we could estimate a possible intrinsic polarization of the jet radiation only of 15%, which is quite high and suggests for a moderate alignment of the magnetic field lines at the base of the jet. Now, the last example for neutron stars, it's the case of SAXJ 1808. This system went in outbursts in 2019, and we had a very good coverage of the outbursts with the Las Cumbres Observatory network of telescopes monitoring. This is the I-band curve that we could obtain with our monitoring, and you can see clearly this main outburst phase followed by this reflaring phase here. So we triggered the Very Large Telescope with polarimeter, and here I indicated all the positions of the 9 epochs in which I triggered the VLT during the outburst. And as you can see, we have a lot of polarization detections. Here we have polarization versus time, and the level is always low, and it never exceeds 2.2%, but the significance is excellent, and we reach upper limit of 0.2% in some cases. And considering that SAXJ 1808 has been already observed to emit jets in the past during outbursts, we thought that it was possible that the low degree of linear polarization could be due to synchrotron from a jet. So we just had to demonstrate it. And to do so, we first built this color magnitude diagram, which is V magnitude versus V minus I color using the LCO data. And here with numbers, I indicated all the polarimetric epochs that are almost simultaneous to the photometric observations. And we overplotted this black body disk model here on top of the data. There are several behavior in this plot. Epoch 1 at the beginning of the outburst is very near to the black body model. Then during the main outburst, instead, we have the strongest jet contribution because you see we are redder and brighter with respect to the black body model. And then during the initial decay, the jet is still there, but less dominant with respect to earlier. And then in the referring state, we are back, almost back to the black body model. So we tried to explain our polarization observations in terms of jet emission, building this figure, which shows polarization versus V minus I jet, that is the observed V minus I color after the subtraction of the disk contribution to the color. And a clear correlation is observed with low levels of polarization corresponding to lower contribution from the jet. So there was no doubt at that point. The polarization that we detect is due to the emission of jets. And in particular, the very low level of polarization that we measure is indicative of tangled magnetic fields at the base of the jet. Let's now look at a few quiescent systems very rapidly. We have already heard from Alex's talk a couple of days ago that jets can be observed in quiescence. Quiescent X-ray binaries typically have softer X-ray spectra than the hard state systems, and also outflows with weaker particle accelerations. But in any case, some radio detections of jets have been reported, like in the case of these systems listed here. And so what we know is that jets are weaker in quiescent X-ray binaries, and also electrons might be dominated by non-relativistic energy distribution. So the spectral energy distribution is typically steeper with respect to the optically thin synchrotron emission of jets that are observed for systems in outburst. So we have a few evidences of jets emission in quiescence in the broad band spectral energy distributions, like in the case of A0620, sorry, where this broken power law was needed to explain the low frequency emission, and this is exactly the typical broken power law of a jet. And then we have this neutron star, XTJ1814. Please notice that here on the x-axis we have wavelength and not frequency, so it's opposite to what I showed you earlier. And this I-band excess in the optical was observed during the outburst and was interpreted as due to a synchrotron from a jet, while these three SEDs here have been acquired in quiescence in 3 different epochs. So we can see that the I-band excess was still present in the first epoch in quiescence, and then faded progressively, thus showing that the jet was likely still contributing in the optical for a while after the end of the outburst.
4 minutes.
Mm-hmm. In terms of polarization, some observations have been performed for the microquasar A0620 in the near infrared and in the optical. Very low polarization was measured, 1 to 2% in the optical and 0.5 to 1% in the near infrared. You can see it here in this plot where polarization versus frequency is represented. The optical polarization, moreover, was found to vary with the orbital phase, so it was interpreted as due to Thomson scattering in the disk. But interestingly, if we look at this graph here with polarization angle versus frequency, you can see that the near infrared angle, polarization angle is different from the optical one. So this was suggesting that the origin of the near infrared polarization was different, possibly synchrotron from a weak jet. And it was this interpretation was also supported by the spectral energy distribution, where the authors found a contribution of the jet to the K-band flux from 8 to 37%. So considering, so they measured the polarization, they could compare, the polarization angle in K-band with the known angle of the jet axis. And also in this case, they found that the magnetic field is parallel to the jet axis. And considering that the jet is contributing to 8 to 37% in K-band, this means that the jet is likely 3 to 18% polarized in the infrared. So also in this case, the magnetic field at the base of the jet is just moderately tangled. Very last thing, neutron stars in quiescence, they are very faint, so it's difficult to obtain polarization detections in quiescence. We made a few attempts with different sources, and in the end, we detected the linear polarization for the transitional millisecond pulsar PSR J1023. The polarization is very low, around 1% in the optical. But and interestingly, as you can see here, we found this hint at orbital modulation of this polarized signal. So then we looked at the SED, and also in the SED, there's no signature of jet emission, as you see in the infrared. So in the end, we interpreted our polarization detection as due to Thomson scattering in the disk. This is the state of the art, everything we know about polarization of X-ray binaries. I know it's not a lot. We are doing our best to contribute to the field, as you can see, especially in the last few years. And well, I really hope in the near future we will be able to add more rows to this table. So to summarize, I hope I've convinced you that near infrared and optical is a very good window in order to study the emission of jets in X-ray binaries, and in particular using the polarimetry that is clearly a powerful tool to probe the structure of the magnetic field in the jet. There's a strong need of dedicated instruments for these, especially in the near infrared and possibly at telescopes of the 8-meter class, because we need very good signal to noise for polarimetry. It would be also good to have short exposure times if possible. And also I would find it very interesting to look for cross correlations between fast time in polarimetry and X-rays, but again, we need a proper instrument for this. And I just suggest you all to stay tuned, because it's really likely that X-ray polarization missions in the future will provide further information for us. So thank you.
Thank you very much. Yuri was definitely the first one here in the room who raised his hand.
Thank you. It seems you have consistently ignored the work that is done in our group. I'm just reminding the audience here that there are other papers published on polarization from X-ray binaries by, for example, there is a paper by Kosenkov on V44 Cygni, and there is a Japanese group published papers on the same object, where at the same time with the paper published at the observation discussed in the paper by Shahbaz, two groups consistently see no polarization, and 4% polarization that was discussed in this review is can be rejected by two independent observations. One should also note that our groups and Japanese colleagues, they have systematics or instrumental polarization on the level of 1/100% or so, while the results published in Shahbaz by TNG telescopes and the polarization, the instrumental polarization is more than 3% there. So clearly there's some inconsistencies between the results presented in this review and published by other groups. There are also a couple of papers on MAXI 1820 plus 070 published by our group. There is a paper by Alexandra Veledina, the first author, and Ilya Kosenkov, who find polarization in the optical infrared bands with the wavelength dependence completely inconsistent with the emission from the jet. So I would like to notice that audience here should know that there are clearly the biased view are presented in this review. Thank you.
You want to answer this?
Well, actually, I totally forgot to mention that I just saw your paper a few days ago in the archive about MAXI J 1820, and I didn't have the time to go deeply into this, but well, I didn't want to ignore your work as well. It's just well, I found it very interesting. I was actually hoping that you could discuss something of the results obtained in that paper in the discussion that you're leading later. Well, I also know, for example, for J1023, recently there was another paper showing polarization results, and well, they didn't find the orbital modulation that I was showing, but of course, as you can see, it is not really well, the confidence level of this fit is not excellent. So this is just a hint at the modulation. So yes, of course, this is just a partial view, but well, polarization is not really an easy field. So there can be different interpretations.
We have time for one quick question by Maria Diaz-Trigo online. I would like to ask the others to ask their questions in the Slack, please, because we're already slightly over time.
Okay, hi, Cristina. Very quickly, is somehow a bit related with one of the comments that Yuri did. I was wondering about the systematics on your measurements. So the statistical significance is very high, as you mentioned, but I don't have a good handle for, you know, what the systematics are. And I was wondering whether you know well about the systematics and whether you can control them or measure them by doing, you know, polarization measurements simultaneously with two different instruments to control on these effects.
Well, yeah, there are a lot of systematics. I mean, the most important one is the instrumental polarization that is normally induced by the instrument, but this can be well modeled. There are several groups like Class Viersema group or Stefano Covino in Italy who are who work on modeling the instrumental polarization, and it can be also high, like a few percent, similarly to what we measure for as intrinsic polarization of this coming from the source. So it's really important to take that, have that under control. And it is possible to know the level of this instrumental polarization thanks to these models, and also from the comparison with the reference stars that are supposed to be unpolarized. But yeah.
Thank you. Let's thank the speaker again.